Dr. Ranjani Parthasarathy is a professor in the Department of Information Science and Technology, Anna University. Her area of specialization is computer architecture and networks. One of her special interests is Indian language technology systems. She is actively involved in research in all the areas and has over 50 publications to her credit. She has about 25 years of experience covering both industry and academics.
Welcome to the UGC lecture series in computer science. We are looking at a series of lectures in computer networks. We have been looking at different layers. We will be now looking at the application layer, and in the application layer today we are going to take a look at security. If we look at today's topic in particular, we will be looking at network security, and we will be looking at some of the cryptography related issues concerned with key management, public key cryptography and message authentication. Cryptography we know is the key element in providing security for the network for the different applications which are running on the network. So, we have already looked at a private key cryptography mechanism. Just take a quick overview of that. If you look at the cryptography components, we know that we have encryption at one end and decryption at the other end. So, we have an encryption key which is used by the encryption algorithm. So, plain text comes in, encryption key is used and it generates what is called as the ciphertext. The ciphertext is what is transmitted, and at the other end we have a decryption algorithm which uses the decryption key and takes a ciphertext as input, works on it and produces the plain text. So, in symmetric key cryptography, the same key is used both for the encryption and for the decryption. So, you have the same shared secret key which is used for encryption and decryption, and the algorithm uses the encryption algorithm, decryption at the two ends. Using this shared secret key, it generates the corresponding output. In symmetric key cryptography, what we have is that the same key is used by the sender for encryption and the receiver for decryption. So, the key is shared. So, the main problem that comes here, the challenge that we have in symmetric key shared systems is how can we share this key in a secure manner, because it is important that this secret key is to be shared in a secure manner, which means we need good key distribution schemes. So, how do we actually distribute this key? So, that brings us to the next important topic in cryptography, which is key distribution. So, what are the options that we have for key distribution? One is that a key is selected by A and delivered to B. So, A has to find some mechanism by which it is able to deliver the key to B. It may be through other manual channel or through some other secret channel. Second is that you have a third party which selects the key and delivers the key to A and B. This is another option that we have. A third option is that we use an old key to encrypt and transmit the new key from A to B, which obviously means that they already have some transmission in progress using a secret key, and so we use the old key to encrypt and transmit the new key from A to B. This is a third option. Fourth option that we have is use old key to transmit new key from third party to A and B. So, we are basically looking at two options, two major options here. One is that the key sharing is done by the node A and it is sent, the key transfer is done by the node A and sent to B. The other is that we use a third party which is responsible for transmitting the keys to both the parties A and B. Okay. The normal thing that is used for when we want to try to automate this entire process is that we use a third party. Then this third party in that case is referred to as a key distribution center. So, we take a look at how that is normally done. So, when we look at automatic key distribution, we use what is called as a key distribution center, or KDC it is referred to, and the different hosts that need to communicate with the KDC to obtain the keys, and then they do the communication. Now, every host typically also has what is called as a front end processor, which is responsible for getting this key and then encrypting using that key and sending the data. This front end processor would typically be integrated with the host, but we just show it as a separate component here to understand that there is a separate functionality that is involved. So, if we look at the various steps that are involved with this in an automatic key distribution scheme with the help of a key distribution center, then we will look at the functions of each of the components there. So, if you look at the key distribution center, now this one determines which systems may communicate and provides what is called as a session key for that connection. That is, for a session of data communication, it provides a key. Then as I said, the front end processor is the one which performs end to end encryption and obtains the keys for the host. Then we talked about the session key. Let us understand what we mean by the session key. Now, a session key is used for the duration of one logical connection, and it is normally destroyed at the end of the session. So, which means that if you used a particular key for a session, we do not normally use the same key for a next session. For next session, we obtain a different key. So, that is what we mean by a session key, and the session key is the one that is used for actually sending the user data during that particular session. In addition to this is also a permanent key that is used. This permanent key is the one that is used for distribution of keys. So, which means that once is a permanent key available and this permanent key is the one that is used for distribution of keys, then using this permanent key you distribute the session keys, and for every session we use a new key and use that for data transmission. So, the idea is that since we are using different keys for different sessions, even if you are using even if the algorithm is kind of broken with for a particular using one session's data, the same key cannot be used for the next session because it is not being used for next session. So, you cannot use that key to derive the data that is used in a second session. So, for session to session we keep changing the key, and this happens with the help of the key distribution center. So, this is normally a mechanism that is used. So, we can now understand the various steps that are involved in this. So, typically what happens is the host sends a packet requesting a connection, and that goes to the front end processor. The front end processor now may buffer that packet and will ask the KDC for a session key. That is a step 2. Then the KDC responds by giving a session key to both ends that are required, that are participating in the communication. Once it happens, then the front end processor can transmit the buffered packet after encrypting it using this key that it has obtained, which is a session key that is obtained from the KDC. Then the communication takes place. At the end of this communication, the session key is destroyed. So, this is what happens in the automatic key distribution mechanism. Now, one of the solutions to this key distribution problem is the use of public key systems. Now, we will take a look at what we mean by a public key system. In public key systems, or what we call as public key cryptography, the operation is as follows. We have again an encryption and decryption process. In the encryption and decryption process, what is normally done here is one key is made public, that is, it is made known to all, and this key could be used for encryption. The other key is kept private, and that is used for decryption. So, we are talking about two keys here, one public key and a private key. Since one key is made public, we refer to this as a public key mechanism, okay, and this public key is the one that is normally used for encryption. So, which means if there are two entities that need to communicate, if B wants to send data to A, it uses A's public key to do the encryption. Since the key is public, everybody has access to it. So, B knows A's public key, so it uses that for encryption. But this encrypted data can be decrypted only by A, because only the private key can be used for the decryption. So, A will use its private key and decrypt the data. Now, note that nobody else will be able to decrypt the key, decrypt the data, because only A will have the private key, right, and you need that private key for doing the decryption. Okay. So, if you look at the operation, what we have here is that it becomes infeasible, as I said, to determine the decryption key given the encryption key and the algorithm. Now, this is the strength of the public key based encryption algorithms. The algorithms are designed in such a way that it is infeasible to determine the decryption key given the encryption key and the algorithm. Actually, either key can be used for encryption and the other for decryption, but the way it is used for secure data transfer is that we use the public key for encrypting and private key for decrypting the data. Okay. So, if we look at the steps that are involved, this is what would happen. First, the user generates a pair of keys, and the user places one key in the public domain, and to send a message to the user, you encrypt using the public key. The user decrypts using his private key. Okay. So, if you look at this entire picture, it kind of tells you what happens. So, Alice is the one who needs to transmit data to Bob. Okay. So, what Alice does is, it uses Bob's public key. Now, Bob's public key is made available to all, right, to the public, it is made available to the public. So, he uses she uses that public key to encrypt the plain text that she has. So, that gives you the cipher text that is being transmitted across the network, and it is decrypted using Bob's private key. Note that Bob has two keys, public key and the private key. So, private key is the one that he uses for decryption and gets the plain text. So, this is what happens in public key cryptography mechanisms. Now, what is important here is how do we choose these encryption decryption algorithms, and so that this encryption and decryption can take place using two different keys. So, if you look at these public key ciphers, the most common public key algorithms that are used are RSA and DSA, and out of these RSA is unrestricted and popular because its patent has expired. RSA stands for the names of the authors who invented or who kind of came up with this algorithm. Rivas, Shamir and Adelman. It stands for R, S and A, stands for these three people who discovered this particular algorithm. So, if you look at the basic idea that is used in this RSA algorithm, it goes as follows. The basic idea is this. So, first what we do is you find two large prime numbers P and Q, preferably at least 256 bits. So, you can see that we are looking at two large numbers and these two numbers are prime. Okay. We are finding two large prime numbers P and Q of at least 256 bits. Second step is you choose a value of n, which is a product of P and Q. Now, n is of the order of 1024 to 1536 bits, a pretty large number we are looking at. Then you find E such that E and P minus 1 into Q minus 1 are relatively prime. The product of P minus 1 and Q minus 1 have to be relatively prime, and that is your E. E and this P minus 1 into Q minus 1 are to be relatively prime. This is the third step. Fourth step is to determine a value D, which is equal to e to the power E inverse mod P minus 1 Q minus 1. That is, D into E mod P minus 1 Q minus 1 should be equal to 1, right. So, this is how we determine the D. That is, if you take D into E mod P minus 1 Q minus 1, it should result in a value of 1. Okay. So, this is how we calculate the D. Then, for any message M of size which is less than n, your encryption is done using m to the power of E mod n. Now, this will be the encrypted message. C is your encrypted message, which is you take the message which is less than size n, raise it to the power of E and do a mod with respect to n. The decryption is done in the using this method, in this algorithm, this formula. M is obtained by getting C raised to the power of D mod n, right. So, this is the encryption decryption mechanism that is used. Now, E comma n is the public key and D comma n is the private key. So, the public key actually is this pair of numbers E and n, private key is D comma n, right. So, this is how we come up with the public key in the public key and the private key in the RSA algorithm, and this is how the encryption and decryption are done. You can see that this involves a lot of computations, right. We are talking about mod, we are talking about raising to a power, you are looking at prime numbers and so on, and you are looking at large prime numbers. So, this is a very computationally intensive algorithm. There is lots of computation needs to be done for this algorithm. Okay. So, the security of this RSA algorithm basically depends on the difficulty of factoring n. That is, given n and the public key, you cannot decipher the private key. That is the strength of this algorithm. So, the security of this RSA algorithm basically depends on the difficulty of factoring n. Remember that we got n as the product of P and Q. So, n is equal to P and Q. So, if I factor n and get my P and Q, then it is easy for me to decipher the whole thing. So, the strength of the whole thing is in making sure that you cannot factor n very easily. Okay. So, typically n has approximately 1024 binary digits, so which is equivalent to a 330 digit decimal number. So, factoring such a large number is not an easy task. Okay. But the algorithm is very slow, that is one of the disadvantages. So, what we normally do is therefore, it is used for only for starting an encrypted connection. For example, exchanging of a session key to be used with 3DES or Blowfish or similar cipher. That is, we just talked about the key distribution problem, right. So, normally we use the RSA algorithm for the initial process of distributing the session keys, and then during the session, that is for the actual data transfer, we may use a simpler algorithm like the 3-DES algorithm or one of the symmetry key based symmetry key based encryption algorithms. Okay. So, this is how we use the RSA protocol. Okay. We will take a short break now and come back and continue with the details. Welcome back after the break. So, we were just looking at the RSA algorithm. So, I will just take you through an example of the RSA algorithm. So, let us take a look at this picture here. So, let us say again Alice talking to Bob. Now, the public key private key pair that we are talking about. Now, 119 is your n and 5 and 77 are the D and E that are being generated. Okay. So, 119 comma 5 is the private key that is made available, and the corresponding private key is 119 comma 5 is the public key that is made available, and 119 comma 77 is the private key of Bob. So, now let us say A wants to transmit a data f, right, which is the plain text. Let us say the value is 6. So, the operation that is to be done is you do 6 to the power of 5 mod 119. 6 is the message, right. So, message to the power of the value D that is used here 5 mod 119. 119 is the value n. Okay, so, let us say that results in a value 41, and 41 is the cipher text that is being sent. On the other side, what we do is this 41 is taken, you raise that to the power of 77 and then take a mod with respect to 119. So, that will give you back your 6, and that is the plain text that is deciphered. Okay. So, this is basically how the RSA algorithm works. As I said, public key algorithms are more efficient for short messages, because as we saw there is a lot of computation that is involved in this particular process. But there is an added advantage to RSA algorithm, which is that it can be used for authentication or what we refer to as digital signatures. Okay. So, what we do here is we use the reverse process. Now, I told you that in for normal encrypted based communication, the public key of the person is used for encrypting the data, and the private key will be used by him for decrypting the data. This is for secure communication. Now, if we do the process the other way around, that is, I use the private key for encrypting the data and I send my data, and my public key used for decrypting the data, then since the data is encrypted by my private key can be decrypted only using my public key, it is an authentication that the message has come only from me, right. So, we can use encryption using private key as a digital signature. That is like saying I am digitally signing it, saying authentication that this is sent by me. So, let us look at that process. So, what we are talking about here is the sender encrypts the message with their private key or his or her private key, okay, and the receiver can decrypt using the sender's public key. Now, remember it is a public key, so it is available with all the receivers. So, a receiver can decrypt using the sender's public key. Okay. So, this authenticates the sender, who is the only person who has the matching key, right, because if I can decrypt the data using the public key, it means it should have been encrypted only using the private key, and that private key is available with nobody else other than that particular sender. So, if I am able to decrypt using the public key of A, it means that the data actually came from A. So, I have authenticated A. Now, note that this does not give privacy of data, because it was encrypted using the private key and it is sent. So, that and it can be decrypted using public key is available to all. So, privacy of data is not ensured by this mechanism, but authentication is ensured. Okay. So, we do not get privacy of data because the decrypt key is public. So, remember that. Okay. Now, so that brings us to understanding how this message authentication is normally carried out. Now, RSA being used for message authentication is a very expensive process, because remember that RSA itself is an expensive algorithm, but can be used for authentication as well. So, we need to look at other schemes by which the authentication is normally done. So, we looked at secret communication using private key and public key. We also said the public key can be used for message authentication. Now, we will take a look at other schemes which are used for message authentication. Okay. So, what is the message authentication problem as such? Okay. Authentication is to allow the receiver to verify that the message is authentic. Again, what do we mean by authentic? It means that the message has not been altered. Second, that the message is from the authentic source, and third, you are able to maintain a message timeline, that is the message does not come too late, right. So, those kind of things have to be ensured. So, this is what we mean by saying that the authentication has to be ensured, that is you may ensure that message is not altered, make sure that the message is from the authentic source and that the message timelines are met. Okay. So, how do we do this authentication? Again we can use encryption for authentication, right. So, here what we do is we assume that the sender and receiver are the only entities that know the key, and the message includes an error detection code. Okay. Now, this error, how we arrive at this error detection code, we will take a look at that shortly, but some code is sent along with the message. So, message includes an error detection code, it also includes a sequence number and a timestamp. Okay. Now, the sequence number and timestamp are used to ensure the timeliness of the data. Okay. So, we add these three as part of the message, and then we use a key to generate what is called as a message authentication code. Okay. So, what we do is now we generate an authentication code which is called the message authentication code, right, based on the shared key and the message. Okay. So, the common key, as I said before, is shared between A and B, and now since only the sender and receiver know the key, so the receiver does the same computation at the other end, and if the code matches, that is it calculates the code, and if the code matches, then the receiver is assured that the message has not been altered. It is assured that the message is from the alleged sender, and if the message has a sequence number, remember we put a sequence number and a timestamp. So, if you have a message, if the message has the sequence number, then the receiver is assured of the proper sequence as well. Okay. So, we have achieved our authentication that we are looking for. Okay. So, typically this is what is done. You take the message and it is sent to a message authentication code algorithm, to which the secret key k is being used, for which the secret key k is also being used. So, you use key and the message by this algorithm, MAC algorithm, and you generate a message authentication code. Now, this message authentication code is sent along with the message. Okay. This is transmitted, received at the other end, and again the same information is used and given to the MAC algorithm along with this secret key which it has. So, k key with this MAC code and the message. Now, this will generate another, that is it will use the same message M and this key, use the same MAC algorithm, generate this code. Now, you compare these two codes. If the two codes match, then you know that your message is authenticated. If there is any difference here, if the message is altered, then this code will not match this code. So, you know that the message has been altered. Okay. So, this is what is done is in message authentication using a secret key. Okay. Now, you can also do authentication without encryption, which means that I do not have to worry about sharing a secret key. Okay. So, how do I do message authentication without encryption? Okay. So, what we do here is we generate what is called as an authentication tag. Okay. Some code has to be generated. So, we just generate an authentication tag and append it to each message. Okay. The message is not encrypted. Okay. And what are the cases in which this kind of system will be useful? This is useful when you have messages which are broadcast to multiple destinations. Then you can have one destination responsible for the authentication process. Not everybody has to do it, one destination may be responsible for the authentication process. Second is when one side is heavily loaded. Okay. So, then if you were doing encryption, encryption would add to the workload, because we know that encryption is a more computationally intensive process. So, we do not want to add to the workload. So, we go for an encryption less authentication mechanism, and you can authenticate random messages, that is another possibility. Third is when you have programs authenticated with without encryption, they can be executed without decoding. See, otherwise if I do encryption, I always need to decode before I execute it. So, you kind of, if I do not use an encryption mechanism, then it becomes easy to immediately start using it. So, these are situations where we go in for authentication mechanisms without encryption. Okay. So, how do I come up with this particular code or the message authentication code or digest that I talk about when I am not using encryption? So, we need to take a look at that. So, we use what are called as one-way hash functions. So, let us look at how these one-way hash functions are derived. Okay. What happens in this one-way hash function is that it is a function such that it accepts a variable size message and produces fixed size tag, or what is called as a message digest. Okay, this is our code or whatever that we are talking about. Normally we use the term message digest. Okay. So, the advantages, as I said, of authentication without encryption is that encryption is slow, so we are getting a faster process now. Encryption is hardware expensive, so we are saving on that, and encryption hardware is optimized to large data, and the algorithms, the encryption algorithms may be covered by patents, so in which case we may not get access to them, and algorithms are also subject to export controls, again we may not get access to them. So, this mechanism of using a one-way hash function in order to do the authentication process turns out to be a faster and cheaper mechanism. Okay. So, how do we do this? Now, we can also use one-way hash along with the secret value, the different ways in which we can use these one-way hash functions for authentication. This example is using a hash function and a secret value. So, let us look at what we do here. Now, I have a message plus some secret value. Okay. Now, the secret value, I take this message plus the secret value and do this hash function. Okay. So, this function basically is is a one-way hash function, which means that takes a message and generates a hash. From the hash, it is not possible to generate the message. Okay. Which is why we call it as a one-way hash function. So, you take the message plus the secret value, do a hash on that, come up with the hash code or the message digest. Now, this message digest is sent along with the message. You take the message and the digest and send it. On the other side, what I do is I receive the message and the digest. Now, I already have a secret value that I know. So, I take the secret value, add it to the message, compute the same hash function, arrive at the hash code, check whether the hash code that was received and the hash code that I have derived now are the same. I compare these two. If they are right, if they are the same, then I know that authentication is achieved, otherwise I know that some contents of the message have been altered. Okay. So, this is one way in which the hash function can be used. Okay. Now, when you talk of secure hash functions, we say that a hash function must have the following properties. It can be applied to any size data block, but it should produce a fixed length output. It should be easy to compute and it should not be feasible to reverse, and it should not be feasible to find two messages that give the same hash. Okay. So, these are the properties based on which hash functions are derived. There are mathematical mechanisms that are used to derive such hash functions. We need not look at the details of those, but remember that these are the properties that the hash function should have. Now, an example of a secure hash algorithm is the SHA-1 algorithm, secure hash algorithm as it is referred to. Now, this uses input messages which are less than 2 to the power of 64 bits and which are processed in 512 bit blocks, and it outputs a 160 bit digest. Okay. So, that is given a 2 power 64 bit message, it will generate a 160 bit digest. So, this 160 bit digest is transmitted along with the message. Okay. This is how the SHA algorithm works. Okay. So, to summarize, what we have looked at so far is we have looked at key distribution schemes and we have looked at a public key encryption algorithm, specifically we have looked at the RSA algorithm. We have looked at how the public key encryption mechanism works and we have seen details of the RSA algorithm. We have also seen how RSA can be used as a digital signature. Okay. Then we have looked at message authentication mechanisms with and without encryption, how a message authentication code has to be generated, and then we have looked at how hash functions are used for doing this message authentication. Okay. So, questions to look at what we have covered today. Question number 1, what are the different ways in which a secret key can be distributed? Question number 2, what is meant by public key system? Question number 3, what is the basis of the RSA algorithm? Question number 4, what is meant by authentication? Question number 5, how can RSA be used for authentication? Question number 6, what is a MAC? Question number 7, why are one-way hash functions used for MAC? With this basis of cryptography and algorithms, we are now ready to look at how these algorithms will be used in network security protocols. Thank you.